Good afternoon, everybody. Thank you for joining us once again in our webinar. Today, we are going to talk about production simulation models and digital twins in mining sites. And for that, we have here our colleagues from Mintek. So whenever you want, the floor is yours.
Thank you so much, Lorena. Hi, everyone. Thank you so much for joining us for this talk or this workshop. My name is Michael Odidi, and the title of this presentation is The Development of a Digital Twin for a Quarry Plant. So I'm here with my colleagues. I'll allow them to introduce themselves. So we can start with Dr. Sandile.
Good afternoon, everyone. So I'm Dr. Sandile Nkwanyana. I'm part of the team. I'm coming from a minerals processing group. So I'm more involved in test work that's needed for this work or for this project. So yeah, thank you. And next question.
So good afternoon, everyone. I'm Dr. William Shipman. I'm involved from the software side. So you'll see I'll be talking about how we connect live data from the plant with the simulation that my colleagues have been working on. Thank you for joining us.
Yeah, thanks, everyone. So without further ado, I'm going to begin the workshop. So of course, this is DigiEcoQuarry. So our project actually forms part of the larger DigiEcoQuarry project. And I think you probably already know, but just to reiterate, this is an EU initiative that involves various industrial and academic partners that are involved in the aggregate industry. So you have different organizations, you have a NIFA, you have a CA, you have Chalmers University of Technology, you have different quarry plants like Holcim and Hansen, and you also have research institutions and organizations like Mintek that are actually involved in this project. Now, the aim of the project, as the name suggests, it focuses on quarry plants. And so we identified four broad sort of areas or four broad stages of the quarrying process flow sheet. So we have your extraction or your fragmentation, which involves your drilling, your digging, your blasting. You then have your transportation of this fragmented material from the excavation site or from the site in which you've obtained the material, and you transport these materials to the actual processing site. And the processing site is typically consists of your comminution circuit, where you have your crushing and your grinding and your reduction of your particle size distribution. And this then is then fed to your classification, where you have different screens and you have your stockpiles, where you begin to, stockpile your product sizes for commercial sale and things like that. So in this project, we have different colleagues and partners that are involved in the different stages. So you have those that are involved in trying to optimize the extraction stage, for instance, looking at blast modeling and the selection of different explosives. And you have those that are involved in the transportation stage, looking at ways of making this process more efficient in terms of transportation of the material. So looking at your fuel efficiency, looking at making the whole transportation phase more safe for the workers and things like that. And then you have those who are more involved in comminution and product classification section. So this is exactly where Mintek is actually focused on. So our work mostly is focused on looking at the comminution circuit and looking at the product classification circuit as well. So now just to give you more of an idea as to what we're doing, we're actually working together with one of the quarry plants. And the aim here was to optimize one of their flow sheets, or sorry, a section of their flow sheets. And so just to give you the broad overview, it begins with the feed material that is sent to a storage bin. And this material is then sent to a cone crusher. And the cone crusher, of course, reduces the size distribution. And the crusher product is then sent to a 3-deck vibration screen. You then have the undersized material from this screen that we would then, for the purpose of this simulation, we would say this is a product stream. You then have the bottom deck, you then have the middle deck, and then you have the top deck, which is then sent to another screen. And then the bottom size here can also be a product stream. And then the oversize can either be recycled back to the storage bin so that it can be recrushed, or you can then have a separate sort of oversized product stream if it is of economic value. So it depends on whether or not these streams are of value. So this is the flow sheet that we intend to optimize. And the way we went about this was to create a digital twin of this actual process. And in order for us to accomplish this task, Mintek actually has different divisions that are working on this project. So we have the Mineral Processing Division, which I'm sure you heard from my colleague, Dr. Sandile. So here they were involved with the analysis of the quarry feed material. They were looking at the physical characteristics in terms of the bond work index, in terms of the particle size, distribution, single particle breakage test, the selection of the breakage function. Then you have those at HMD, the Hydrometallurgy Division, which I'm representing today. And so we were involved in the development of the digital twin, sort of the skeleton of the digital twin. So this involved the selection of the crushing and screening models, your model calibration, your model optimization, and also the actual flow sheet model as well. And then we have the Measurement and Control Division, which Dr. William is representing today. And they are involved in the development of the communication interfaces. So this looks at the measurement and storage of data, the digital twin simulation service, the user interface design, as well as data connectors, because as you know, we're going to be transferring a lot of data from the plant to Mintek and to the data lake and things like that. So that is what the Measurement and Control Division we're actually working on. So without further ado, I'm going to then hand over to my colleague from the Mineral Processing Division, Dr. Sandile, who's going to then take you through the work that they did for this project.
Okay. Thank you, Michael. So yeah, as he mentioned, we were just involved with just the characterization of the quarry rocks that were given to Mintek for this work. So the main test that we did was the bond crushability work index test, which feeds into the simulation work that Michael and William are working on for the calculation of the power consumption and the specific energy. So all the optimization efforts that they are putting in, they need to have a look at the specific energy. So it's critical for them to have an understanding of the hardness of the material, and hence we had to do the work index test for them. So just a brief overview of what the test is all about. I'm sure many of you know this test. The test was developed by Bond back in the 60s, 1961. It just has two, comprises of two, back in the days, it was comprising of two opposing 30-pound hammers that come together in action by rotating the two wheels on opposite end, as you see on the left of the screen there. The wheels are reinforced with some steel bands around it. So when you lift up the left-hand wheel, trying to rotate it in a clockwise direction, then it's synchronized with the right-hand wheel. And so it's being lifted up. There are two hammers there at the center, which also get lifted up. So when you release the bands, then the hammers will come back and hit at a 6 o'clock position. And by knowing the heights that they were lifted at, you and be able to determine the potential energy that was used to effect breakage on the specimen there. So that was the ancient apparatus that was used by Bond. On the right hand of your screen, there's the one that we now have at Mintek. It's much more modern, but it's still loyal to the Bond's original idea. So as you can see there from the center, on your right, the specimen is spaced there on the center, so the two hammers come and knock at it. So what you do, you keep on just adjusting the heights of those hammers until you get just the minimum threshold that is required to just break the rock. So the minimum energy that is required to break the rock. And from that, you are able to work out what will eventually be the bond crushability work index. So Michael, if you can maybe move to the next slide. So from lifting up those hammers by just adjusting the angle of the wheels, from that the Mintek apparatus, one can then determine the energy that's absorbed at impact using that equation 1. So it's the input on equation 1 is just the angle. That's the wheels that you read from the wheels, which is taking into account how much the hammers were lifted. So from that you can work out the energy. Once you have that energy absorbed in impact, then you can work out the impact strength, which requires you to have the thickness of the rock So as you probably see on the first slide, the rock is facing, it's mounted on that center in such a way that you've got the smallest side of it's facing upwards. So the smallest dimension facing upwards. So once you have that impact strength, then you can work out the index there. There's a calculation, of course, that goes into how you derive that 53.49. It's an empirical correlation, but eventually arrive to that. So then you can work out the work index. So we did that test, and of course, then Michael and them, they will use that number to work out the specific energy, and hence the power that is taken expended on the crushers to do the job. But we will understand that there are many other fudge factors that need to be put in there. It's not as straightforward as equation 4 when you work out the specific energy. There are some other factors that need to be taken into account because yeah. So on your right there on the screen, those are just the numbers that we got to characterize the material. So on average, we are sitting at about 60 kilowatt hours per ton metric tons for the work index of the crushability work index of that material. So it's ranging on just a medium-sized, it's medium. The hardness of it can be characterized as relatively medium range of hardness. So yeah, that's what we did for the bond crushability work index test, and then the numbers were used on simulations, and hence the optimization work that has been done. The next thing that we had to do was the breakage distribution function. So on the simulation software that's being used for this project, which is IDS, for the crusher simulations, you need to have a distribution function inputs there. So we followed the much more common breakage distribution function from Kelly and Spotson's work back in the early 90s, but it's also much more common from Austin and Kimple's work. So that's distribution function. Even though it was originally developed for grinding work, but it has been applied by many people on crushing work as well. So what's the breakage distribution function actually is looking at? It's looking at the BI, B value there. It's just looking at the average mass of daughter fragments that's are smaller than size X that were generated by a single impact event from a particle size of Y. So as I'm saying, it's the progeny size distribution of generated by a single impact event on the particle. So you then implicit from what I'm explaining is that you need a number of particles to be broken for you to obtain an average result of this breakage distribution function. But just to emphasize a point, this function, it's not exactly what is the progeny from a crusher, but rather because we understand that the particles get rebroken in successive intervals as they move from the feed end towards the product end on the crusher. But this just clearly just defines a single impact event, what is the progeny distribution that's been generated from there. So the way we approached this to get the parameters in this function is by performing a single breakage impact test. So the test that we performed, and I can move to the next screen. So we had to perform single impact breakage test for us to be able to get data that we can fit into this function and have the breakage distribution function parameters. So we use a drop weight tester at Mintek. I'm sure many of you are fairly familiar with it, supplied by the JK Tech. So we use that. So we did several tests on that, and we're able to get data that we fitted on the function. And on your right side, we show you the response of the parameters for different current particle sizes. So you see the blue and the orange lines. You see it's evident that the parameters are not sensitive to size that we were testing from about 60 millimeters down to about 30 millimeters. the sensitivity of the breakage parameters to those different sizes is not significant. But you will see that the N2 parameter seems to be like wobbling around. But we were not concerned by that behavior, because we understand that the K value, which is the fraction of the material that can be characterized as core, as fine. So so there is I forgot to mention this earlier. So K represents the fraction of the feed material that is can be characterized as fine. So 1 minus K is a fraction of the material that can be characterized as coarse. But if you look at the K value there, it's relatively sitting at just close to 1. So that means most of the material that we're receiving can be characterized in one class. So hence then the 1 minus K is the second term in equation 5 is not important. So the K parameter, then the wobbling of it is not a good concern to us. So yeah, that's the approach we follow to get the breakage distribution function. And as I mentioned earlier, this is an input to the simulation software that my colleague is using to optimize, to simulate and hence optimize the crusher plants at Holcim. Just one last thing to mention here is the fact that we understand that there are many functions, breakage distribution functions that one can apply to a crusher. One approach is the one that we're presenting here, but another approach is that of using the TN family curves that one can generate from the JK Tech data. We could have applied that, we could have taken that approach. The software accepts that approach, but we were limited by the fact that that approach requires a lot of calibration data, calibration from the plant data, which we were not, we didn't have at the time we were doing this work. So yeah, that's just one thing that we just wanted to mention. But as we fine tune the work, we might get data that might allow us to take that approach as well. I think I've said much. Now I'll let my colleague William to continue.
Oh, okay, thank you. So thanks everyone. Thank you, Dr. Sandile, for that presentation. So yeah, I'm gonna now take you through HMD's portion of the work. So we were tasked with actually developing the digital twin. And for those of you who may not be familiar with the term digital twin, it's a digital replica of a physical system or process. So you have your physical twin, so you have your physical process, which would have your different objects, it will have your different equipment. And in order for you to actually formulate a digital twin, you're gonna need to collect data. So you're gonna need to set up measurement devices that will measure key variables, measure key parameters. And so you then collect that data, and that data is now fed into representative models. And these representative models are actually the backbone or the skeleton of your digital twin, because they actually govern how your how these parameters interact with each other. So once you have your data, you then use it to calibrate your your representative models or calibrate your digital twin. And once you've calibrated your models, you can then use the digital twin as a decision-making tool. So you can use it in order to try and advise you on how to optimize your physical twin. So you'll be able to actually look at, certain parameters, the effect of certain parameters, and see, if you can tune them or if you can change them, how that actually affects the processes that are occurring in your physical twin. So in our case, we knew that we had a flow sheet to simulate, so we needed a flow sheet simulator, and we also needed data storage and calibration and validation software. So for the flow sheet simulator, we decided to make use of Ideas by Andritz. So this is a commercially available flow sheet simulation software. And then for the data storage, calibration, and validation, we decided to make use of Microsoft Excel, as it's widely popular and it also has good data exchange properties. So these were the two main softwares that we were using to create the digital twin. So just to give you more of an idea as to the flowsheet simulator, we actually created a flowsheet model of the process. And then to explain how it works, Ideas has a library of different icons, right? So these icons typically have a one-to-one correspondence with actual processing equipment. So in our case, the two icons that were of interest were, of course, the crusher icon or the crusher object, as well as the screen icons or the screen objects. Now, these objects actually have models that are inbuilt into them, and these models need to be calibrated or need to be basically fitted to data from the plant. But just to give you an idea as to the different models that are used, for the crusher modeling, as my colleague has already mentioned, we made use of the breakage function, the BXY function. And for the classification function, for the crusher, we made use of the Anderson-Whiting classification function. So these are the two functions that actually allow us to model the crusher in terms of allowing us to predict the output particle size distribution based on the feed material to the crusher. In terms of the screens, we decided to make use of an undersized to oversized ratio. So this basically looks at the amount of undersized material that reports to the oversized stream. So we wanted to see how efficient these screens are. But upon looking at the data that we obtained from the plant, we realized that the screens at the plants were actually performing perfectly, right? So there wasn't really any undersized material that was reporting to the oversized stream. So at the end of the day, this really was not done because it became sort of redundant because there wasn't really any problems with the screening. We could just assume that there was perfect separation and perfect efficiency. So now when it came to the actual data storage, calibration, and validation, we decided to create different consoles. So we created a calibration console on Excel, and we created an optimization console as well. And basically, these consoles have different functionalities, but their functionalities are actually hidden within the VBA code. So we try to automate a lot of these different functionalities and processes as much as possible in order to allow it to have sort of a more of a, what can I say, streamlined design, so that when users can actually log in, they'll be able to actually use the system without having to go through a lot of the manual fidgeting and changing of variables. So just to take you through the functionalities of the calibration console quickly, we created the breakage distribution function calibration functionality here. So basically, based on the data that you receive from the lab, from the single particle breakage test, we are able to then fit the breakage distribution function and obtain the fitted parameter values. So you have your K, your N1, your N2. So this automates that process for us. So all we need is the raw data from the laboratory test, and we can actually generate the fitted parameters. The next function here is the particle size distribution function calibration. So we understand that at the plant, you may have different instruments that are measuring particle size distributions, and these different instruments are going to have different sort of size classes, or even if it's a manual sieve operation, you're going to have different sieve sizes in certain cases. So we needed to sort of standardize the data that will be fed into the model. So the way we did this was to create, use the SWABREC particle size distribution function and basically fit the data that will be coming in and generate the parameters so that we can regenerate the particle size distribution based on the needs or on the criteria that we have for our model and for our digital twin. We also then have the breakage matrix. And for those of you who are familiar with this basically is derived from the breakage distribution function. And it basically just governs how the size distribution of your daughter particles upon the breakage of your parent particles. So this is sort of trying to look at how the different particles in the crusher actually break. So it's just basically a matrix that governs that based on the breakage function parameters. We then go a step further and you have your product matrix, and the product matrix actually combines the breakage function and the breakage matrix, the information contained in the breakage matrix, in order for you to be able to generate your classification vector and generate your actual product PSD vector. So you then have these different classification parameters that are fitted to your data in terms of the calibration of this function. And then once you have the fitted parameters, you can then use them in your optimization console. We also have the option of looking at, the crusher energy diagnostics. So looking at the amount of energy that is being consumed, looking at the theoretical energy consumption, the actual energy consumption, the crusher efficiency, the power scaling factor, your FAT, PAT, which is basically the size at which 80% of your feed material passes or 80% of your product material passes. And then the bond work index is what was obtained in the laboratory, as you heard from my colleague, Dr. Sandile. So the overall aim of the calibration console here is to calibrate the models in order to make them as representative as possible of what's going on in the actual plant. And once you have your calibrated model, you can then go into the optimization console. So I'm not going to go through the individual functions, but I'm going to summarize it by saying that this ties in basically with the flow sheet simulator. So you have your flow sheet simulator that has the different models, and then you have your calibration console that calibrates the model parameters. And then this is fed to the optimization console, which would then basically allow us to run the simulations using the flow sheet model that we have here. Just to give you an idea as to the results that you obtain. So for instance, running a single simulation, you can then look at your crusher object and look at the particle size distribution of your feed material and look at the particle size distribution of your product material based on the models that we use, the representative models that we're using. You can also then take a look at the screen objects as well to look at the particle size distribution function of the feed to your screens and the products from your screens. And as I've said, the screens were basically performing with like 100% efficiency. So that's why you would notice that the orange line is almost vertical. So basically there is almost like a perfect separation of the material. You can also look at the entire flow sheet, right? So you can just basically isolate your main stream. So you can look at your main feed to the process, and you can look at your different product streams and look at the particle size distribution of these different streams. And this will allow you to sort of see if the PSD is what you are targeting, or if it's off, or allows you to sort of have an idea as to what exactly is going on in your process. So now we didn't want to stop with just a single simulation run. You want to be able to sort of try and optimize your flow sheet. And so the way we thought about doing this was to create objective functions as well as optimization parameters. For the objective functions, we thought of three main areas, right? So you could look at them as key performance indices. So you have your economic sphere, where you're looking at the maximization of your revenue. You have your environmental sort of sphere, where you may be looking at the generation of dust. So you're looking at perhaps reducing the amount of dust that is generated in the crusher. Then you have your energy as well, where you may want to sort of optimize the energy usage of your crusher and try and make it as efficient as possible. You then have your optimization parameters. In this case, we chose three different parameters that we thought were of primary interest. We obviously have the option to add more, but for now we chose the closed site setting of the crusher, the CSS. We also chose the feed throughput, meaning the amount of material that is fed to the crusher. And in the case of the actual flow sheet, we were also looking at the recycle parameter. So what happens with the recycling ratio? If you were to recycle your oversized material back to the crusher, how does that actually affect some of your objective functions? So in this case, this is just the Excel interface. The actual interface that the user will be exposed to is still being designed, and my colleague, Dr. William, is actually going to take you through that. But for the Excel interface here, we just have some dummy economic data. So we wanted to sort of see how this functionality works in terms of predicting the revenue or the net revenue from the plant. So here we just have dummy economic data. And for the purpose of this presentation, we're going to look at varying the recycle ratio. So we're just going to be looking at varying the recycle ratio. And the other parameters then are going to be kept constant. So this is going to be a single parameter varying optimization strategy, if you want to call it that. So here are the results. So we coded in for the simulation to run 10 times. And in this case, we varied the recycle ratio from 0.2 to 0.8. So 0.8 meaning that you are recycling more of your material back to the crushing circuit, and 0.2 it means that less of the material is being recycled, right? So looking at the effect of your recycling ratio on the product distribution, so you can see here from the simulations that we run that basically increasing your recycle ratio does actually reduce the amount of oversized material that you're producing. So you'll notice that the O/S, which is the oversized stream, as well as the 24/60 stream, you notice that you are producing more of your finer product as you recycle more of your coarser product. So this gives you an indication as to how your product distribution changes with the recycling ratio. You can also look at the fineness modulus. And this then shows that increasing the recycle ratio, meaning that crushing, and feeding in more of, recycling more of your oversized material, the final products actually become finer. So based on the fineness modulus, which actually reduces as you increase the recycle ratio. We can also look at the energy power usage plot. So in this case, we see here that by recycling more of your material, you are making your crusher work a bit more. So you are going to be spending slightly more energy in terms of kilowatt hours per ton, as well as the power usage. We also were able to then generate what do you call it, a dummy revenue plot. So basically, this then tells you that, okay, increasing your recycle ratio, your net revenue is going to increase. But again, this is based on dummy data. So once we have the actual plant data and look at the actual value of the product streams, we'll be able to have a more realistic sort of view of the revenue or the effect of certain parameters in terms of just the revenue based on the amount of energy that is consumed by the crusher and the amount of value that you obtain from the different product streams that you are producing or the different aggregate streams that you are producing. So yeah, so this is what we currently have in terms of the different functionalities and our ability to sort of use the digital twin in terms of generating data and seeing how these sort of parameters affect the process. I'm now going to hand over to my colleague, Dr. William Shipman, who will take you through more of the user interface and all of the things that make this a more sort of comprehensive product. So without further ado, I'll let him take over.
Will you just please? Apologies, we have a little bit of a problem.
I think the mouse is.
So what I'm going to cover, my part, is first I'm going to give you an overview of the system as we've designed it. So a system for getting data from the plant, connecting that with the simulations that you've been hearing about today. Then go into a bit more detail about how the connections actually work, what information we are storing to make our digital twin, and then I'll talk a bit about the user interface design as well. Slide, please. So if we look at the system as a whole, the goals, as I've said, is we want to connect the physical world, so the physical twin, the real crushing plant, to the virtual world, which is the simulator that's developed in Aggregates Sites and which the data for it is stored in Excel. And what we want to do, and the end reason for doing all of this, is to allow our partners to then run simulations and do optimization exercises like what Michael was showing a few slides ago. Next, please. So if we zoom out and look at the entire system, what we have here, hopefully the laser pointer will work. Yeah, you can see this. There we go. I hope you can all see my mouse pointer. So if we start on this side, we have a central service. This is the web service that we are developing, which is the backbone for collecting the data and distributing it to the computing resources that will actually run the simulations. We have a public-facing part of the system, application programming interface, where we can then have so this is what the user interface connects to. So this is what our partners will be seeing. They'll be able to then use that user interface to view data that's collected, select data to recalibrate the model, and as well then run simulations. We also have sources of data. For example, we have Maestro, hope I'm pronouncing it correctly, and they are their system is operating at the crusher. It is the automation system charge there. So we are collecting data from their system, and we are then using cloud services to periodically pull that data and store only that which we need in our system. The DigiEcoQuarry project as a whole has a data lake where all of the partners are sharing information. So we will also have cloud services that will extract data. This could be, for example, simulation results, calibration data, and put that back into the data lake so that we can share it. Lastly, on the far right-hand side, we have computing resources. So this is, we call it digital twin agents. And what these are doing is they're executing simulations. So these are the computers that have, for example, the computer that has Android's ideas installed on it and is able to run the simulation that my colleagues have been working on. And this last bit here is really our administrative interface. So if we could move on to the next slide, please. Okay, so let's talk about the sources of data and the destinations for data. So I've mentioned that we have Maestro. There's also the potential need for manually capturing data wherever an instrument is, for example, not giving information with sufficient accuracy. Obviously, this project is all about digitalization, so we don't want to do a lot of manual capture, but we do need to keep in mind that it may be necessary. The simulation is also a source of data in this system. It provides data in the sense of results from running simulations, model parameters, optimization exercise results. So that is why simulation appears both as a data source and as a data destination, because the information that we store in our system then has to go into that simulator to be able to generate results. We move to the next slide. So if we look at the first data source and the first data destination, so Maestro, the source of data, and the DigiEcoQuarry data lake. Our system is hosted in, or will be hosted in Microsoft Azure. We have a web application, it's the backend, has an API, and backing that is a database. We're then using Azure Functions to do the import and exporting of data. So these functions can, for example, run on schedule, or they can be triggered by different events. So that gives us a lot of flexibility there. Next slide, please. When we look at manual data capture and the user interface as a destination of data as well, the same web application backend connects to a user interface that we are using one of Microsoft's modern technologies, Blazor, to develop that user interface. And the nice thing is that that technology can then works in a web browser, so it can run on desktop PCs, cell phones, be it Android or iOS. And finally, on the left-hand side, we have the actual user's system. Next, please. So you would have seen that the last part was talking about the simulation. That was the last source of data and destination of data. I'm going to talk about that in more detail, specifically talking about these things we call digital twin agents. So if we start out with just what is a digital twin, in this system, we're specifically looking at it as a model of the real world. So you have a model or simulator that is developed in ideas, with Excel being used to assist and being used as the interface. But in principle, there's no reason that you could not in future have simulations developed in other programming languages like MATLAB or Python. And the way in which we've designed this system is to actually keep that in mind. So what you would have is each digital twin agent, these little blocks that are meant to represent a server or a computer, could be sitting in the cloud, or it could be sitting on premises here at Mintek. And it would have the software required to run that particular simulation. All of these agents then communicate via the internet to our application hosted in Azure. So the use case for this is being able to run simulation, for example, saying with our current operations, what should our system be achieving, or to do optimization. And Michael showed exactly there an example of what happens if you adjust the recycle ratio. Next slide, please. So I've talked a bit about the components, but just some of the things that we're storing is model parameters. So these are, for example, K, N1, N2, bond work index, so crushability index, so all of those physical parameters that describe the ore. Then you also, that makes up your digital twin, but then to run a simulation, you have parameters like the feed rate, the closed site settings. We store those separately, but you can reuse the model parameters with many different simulations. And then, of course, we store the results as well. So all of this information here is stored in this database over here on the right-hand side. Okay, next slide, please. I've talked about grouping the digital twins by type, and basically, yes, this architecture allows us to then support many different types of simulations in future. But for the purposes of this project specifically, we're using this one in the middle. I know I've only got the Excel logo here, but just imagine there's an Andritz Ideas logo sitting on the side here. Next slide, please. I've talked a bit about this, but essentially what these agents are doing is, on the one hand, running the steps required to take plant data and calibrate the model, and on the other side, actually executing simulations. Next, please. So I just have the last few slides about the user interface. So as I hinted at before, by using this modern technology, Blazor, by Microsoft, we were able to support both your Windows PCs, Android devices, iOS devices. Really, actually, we're just limited by what has a web browser. As long as it's not something archaic from more than a decade ago, we should be okay. So this gives us this means we have the most, system is the most accessible that it can. To your next slide, please. And one of the things that this brings with it is a responsive layout. So here you just see the layout if you're looking at the desktop application. But if you switch to the next slide, then as soon as we change to a cell phone layout, I want to highlight this is still work in progress, but you can see immediately your menu goes from something being on the side to something hidden behind a very, very common hamburger button. So, and that's a nice thing with using this technology, it does that for us automatically. Thank you, and yeah, I'll hand over back to Michael.
Thank you so much. So yes, that's what we have currently. So as William has mentioned, we're using Excel at the moment, but we do plan to migrate some of the functionalities to more flexible software and more sort of easier to use software. I'm sure MATLAB and Python would provide great flexibility as well as more functionality. Then we also plan to review the different models that are used to make sure that these models are actually representative of what's going on. So this is something that we are planning to develop more and more. And of course, we're not just limited to one quarry plant. We may have to expand the flow sheet or look at different other processes, things like that. But yeah, so currently it is something that we we are happy to be working on. And yeah, we hope that this presentation was useful and informative. So thank you so much for this.
So thank you, William, Michael, and Sandile for the super interesting presentation. I believe there's a question in the chat. Are you able to read it, or do you want me to read it?
I'm able to read the Q&A questions. I've actually got them open here already. So Manuel Gonzalez asked us, hi, regarding the stream data, was it raw data or calculated data? It is very rare to get a perfect stream without any imperfection.
Yes, so that is exactly our initial thought. So that's why we actually had a whole bunch of different models that we prepared. I think we also had the Kara model that we were thinking of using. But when we analyzed the data that was sent to us from the plant, it seemed to be actual measured data from the plant, and the data showed perfect separation. So that's when we decided that there was no point in us using these, sophisticated models if the data that we're obtaining from the plants is giving us this sort of perfect separation. So yeah, we were a bit also shocked, but yeah, it is what we received. So yeah.
Manuel has asked a follow-up question, asking, let me know the stream make and model. I think maybe you would like to buy this perfect stream.
Yeah, so from what I remember from the data, it's HP 200, and I think it's a screen from Metso. So it's a HP 200 vibrating screen, and it's from Metso. But you would need to speak to the guys at Wholesome. So they will be able to really inform you about their screen details and exactly. But it has an angle of inclination of about 18 degrees. I'm not sure of the vibration frequency, and yeah, but they seem to be really happy with it. So I think you can actually talk to them about it, and yeah.
And then our next question is in the Q&A from Anonymous, and he or she was asking if we would be willing to share our presentation. So from my side, I have no issue with that.
No problem.
I also don't have an issue. So
It's still within
yeah.
the consortium, right?
So we will be able to share the presentation. I don't think we gave any IP anyway, so I think it's fine. Yeah,
as long as it's still members of the consortium.
No, I think this is public, so we're outside of the consortium.
Maybe we should talk about.
We'll talk.
Okay, we'll talk about it.
Yeah, we just need to check, and we'll get back to you. But yes, your email is here. Thank you.